Greetings to all. My name is Shivain and I'm from BTech CSC Regular, and today I'm going to present a topic losses in transformer as a part of the BW presentation. So starting with what is meant by a transformer. Transformer is nothing but a device which has two coils, the primary coil and the secondary coil. They both are connected to each other by something known as a transformer core, which is made up of silicon. The primary coil is connected to the AC source, and whenever there is alternating current passing in the primary coil, there is a magnetic field change in the secondary coil, which induces something known as the mutually induced current in the secondary coil, and this all happens because of the laws of mutual induction of Faraday. And we should keep in mind that transformer is a static device. That means it doesn't move, and also the frequencies in both the secondary coil and the primary coil remain the same. Now, coming to the main topic, that is types of losses. First of all, before going into types of losses, we should first understand what is meant by a loss. Well, loss is nothing but the short form of power loss. Now, what is power loss? We know that ideally, that is on the pen on the paper. Transformers have 100% efficiency. It means that if I get 100% input, I will get 100% output. But in real life, due to many factors, the efficiency is never 100. So the factors which affect the efficiency of the transformer and make the decrease the output in the practical life are known as losses. So the losses can be divided into two parts: cold losses and copper losses. Cold losses can be subclassified into eddy current losses and hysteresis losses. So let me start first with the cold losses. Core losses are nothing but disadvantages that occur due to the things taking place in the transformer core. Here you can see in the given diagram that we have the primary coil, as you can see the pointer, and here we have the secondary coil. And these are the primary and the secondary coil are made up of aluminum wires, while this is made up of silicon. The transformer core is made up of silicon. Now coming to the part of hysteresis loss. First, what is meant by hysteresis? Hysteresis loss is nothing but the power loss caused due to the magnetization and demagnetization of the core material. As you can see in the given diagram, here the magnetic flux is passing through the transformer core in this way, in this direction, and again it keeps on passing. But we know that we don't use transformer always, nor it is any time that we don't never use transformers. Transformer are just like any other electrical device. We switch it on and switch it off. When we need it, we switch it on. When we don't need it, we switch it off. Now when we switch on the transformer, the core is getting magnetized. Yes, there is a there is a alternating current induced in the secondary coil, and there is a magnetic field also present in the secondary coil, but also there is a magnetic flux in the transformer core, because the magnetic field in the secondary coil is transformed from the primary coil due to the medium between them, which is known as the core. Generally, cores nowadays are made up of silicon. The reason made of silicon they are made of silicon, I'll be explaining in the last of this video. So coming to hysteresis loss, whenever we switch it on, the core is getting magnetized. Yes, the secondary coil is also getting magnetized, but when the core is getting magnetized and when we switch it off, the transformer, it is getting demagnetized. And when it keeps on happening many times, the quality of the core reduces. That is why the conductance of the magnetic field in the core becomes low, and that is why the secondary coil quality of receiving the input of the magnetic flux or the alternating current quality in the secondary coil reduces. So that is why this whole loss is known as hysteresis loss, because it takes place due to the magnetization and demagnetization of the transformer core. And also coming to the other loss known as eddy current loss. As you can see here in the transformer, sometimes a magnetic field which is of this spiral shape, is formed here in the transformer. And when this is formed, then the magnetic field here in the secondary coil is disrupted by the field here, which is known as the eddy currents. Eddy currents are useful in real life, such as the traveling of trains. Eddy currents are can be seen in real life, such as the traveling of magnetic leveling in the bullet trains in Japan. But here they serve as a loss to the transformer because they disrupt the magnetic field of the secondary coil. Now, why these both losses are called cold losses? Cold losses are also called iron losses. So simply because they both occur in the core. The hysteresis loss occur due to the magnetization and demagnetization of the core, while the eddy current occur here between the core and disrupt the magnetic field of the secondary coil. So let me go with the other loss known as copper loss. Copper loss. First of all, why this word copper is used here? Because it is generally related to the wires that we are using for primary coil and the secondary coil. Here you can see, here we have the primary circuit, and here we have the secondary circuit. Now these wires, as you can see in the circuit, these wires, this coil and this coil and this coil, they all are made up of copper or aluminum wires, or we all know the reason, because they have good conductance of electricity. But as we keep on using them and using them, their conductance decreases, and when the conductance decreases, the resistance increases, and we know that when the resistance increases, heat dissipation takes place. Now when the heat dissipation takes place, we can come to the conclusion that H is equals to I square RT by basic electricity formula. Heat is directly proportional to current square, so the copper loss gives out a heat. So copper loss is proportional to the current square. So this is the mathematical relation between copper loss and the current. Now we can come to conclusion to this loss, that whenever there is electricity flowing in the copper in the transformer, in the primary coil and the secondary coil, the many times heat is generated, and when the heat is generated, the transformer gets overheated, and when it gets overheated, the quality and the materials used in making of the transformer get degraded, as like just like any other appliance, electrical appliance. If we give too much heat to the appliance, the quality and the material of the appliance gets degraded. So that is why, due to copper loss, the appliance material get degraded, and due to cold loss, the core gets degraded. So both losses are very much are a big of a disadvantage for the transformer efficiency. Now coming to temperature effects, not only cold losses and not only copper losses affected, but also the temperature affects the the copper losses and the core losses, which in short can be called together as power loss. Now let me tell you how it is related. Now, as you can see in the given the graph, as the graph is increasing linearly, we can all say the power is also increasing, and the temperature is also increasing. So we can come to the conclusion that temperature and the power loss are almost linearly connected, and thus we can say that as the temperature increases, the power loss also increasing. Thus we can come to the conclusion that increased temperature can result in greater copper loss, and can also result in greater core losses, which decreases the efficiency of the transformer overall. Now, coming to some strategies known as mitigation strategies. Now, what is meant by mitigation strategies? We know that when the losses are being take place in the transformer, there are many other troubles caused. First trouble is nothing but the noise pollution. Second trouble is nothing but heating up of the transformer due to copper losses, and the noise pollution is caused, as we all know. And second thing we should take care is nothing but the temperature. Fourth, and the third thing we should take care is about the stability of the transformer. Now, mitigation strategies are the strategies derived or made due to which we can minimize all the losses and all the disadvantages of the transformer. Some of the mitigation strategies I will be discussing with you now. So for to minimize to minimize the core losses, as given here, core losses, I already told in the starting that silicon core transformer poles are being made nowadays. That is why silicon is a material which helps in reducing the hysteresis loss and the current loss. So that is why silicon nowadays it is used as in making a transformer core. To use the to benefit to reduce the copper losses, we are using something known as a different kind of winding patterns. Windings are nothing but the way we wrap the wire around the transformer core is nothing but that, known as winding. Suppose I have a, this is the part of the transformer core here, and I'm winding my wire around it. So this is known as winding. So this is known as winding. So there different kind of windings are there for different kind of transformer: step up transformer, step down transformer, auto transformer. And according to different transformer and different models, different kind of suitable modeling winding techniques and designs are introduced to reduce the copper losses. Now coming to the one of the major disadvantage, that is nothing but the noise pollution. That is nothing but the noise pollution. Now when the quality of the material is degrading, noise pollution is being caused because it is releasing energy. Power loss means release of power. Release of power. When the power is releasing, it is releasing some energy. When the energy is releasing, it will also make some sound due to basic science laws. So that is why, to reduce these noise barriers, we noise pollution, we use something known as noise barriers around the transformer. Now one more thing to look upon is the structure of the transformer. Yes, we will make a transformer by the primary coil and the secondary coil and the transformer core. But to how sure are we that the structure is very stable? Suppose if any small object hit the transformer, what is a guarantee that it doesn't fall and doesn't break? So that is why you should try to isolate the transformer from the area of common travel, and we should make the structure of using spring type surfaces too, so that it will absorb any shock, any shock due to any collision given to it. Now coming to other thing, for cooling down the transformer, we know that sometimes the transformer might get heated up due to the temperature or due to the copper losses. To cool it down so that the material doesn't get degraded and the quality doesn't get low, we use something known as low noise fans, because when we use fans, they cool down the temperature in the transformer, and thus maintaining quality of the transformer. So now coming to impact on efficiency. And now all these losses and all these things are being discovered because of one thing, and the one thing is nothing but efficiency. Now here in the given formula, you can see that efficiency is nothing but output power by input power. But we know that energy is conserved, so input power will be equal to output power plus losses. And output again, losses are nothing but iron losses, which is nothing but the coal losses and the copper losses. In ideal situation, the losses here given is nothing but equal to zero. So output power by output power will get cancelled, and we will get efficiency equals to 1, and efficiency percent will be equal to 1 into 100, 1 into 100. So that is why the efficiency will become 100%. Efficiency will become 100%. So that, but this is only practical in theoretical cases. In practical cases, these losses take place, as which I was explaining from the past 6 to 7 slides. These losses take place, but we already know we cannot make these losses zero in real life, but we can diminish to them to very low amount, because mathematically, if we go, or even by logic sense, if we go, if these losses are less, the numerator will become equal to the denominator, and thus we'll get efficiency almost equal to 100%, or it will be above 90%. And how to calculate these losses means, we can calculate copper loss by directly knowing the square of the current and the other factors and the other formulas. In by going by logic sense, obviously if the losses are less, the input power is if suppose it is 100%, then the output power is also gonna be approximately equal to 100%. But ideally it will be equal to 100%, but in real life the efficiency cannot never be equal to 100, not as per now. In future, any technologies come, efficiency might be 100%, but not now. So we can only minimize the copper losses by the strategies known as by the losses by strategies known as mitigation strategies. Now, I would like to conclude this video by saying, yes, there are many disadvantages of transformer caused by the losses, but we can decrease the losses and the disadvantages of transformer cost to the public by using proper scientific methods and proper study on the transformers. Thank you.